In this video, we're going to look at how to solve for integrals of the form x to the power of p times some rational function of x from 0 to infinity. So a couple things up here are different than before. So we have the limits are different. Here's 0 to infinity. Before we had negative infinity to positive infinity. In addition, the integrand is different. We have x to the power of p times some rational function of x dx. And also here, note an important thing. P is not an integer, so it's not -2, -1, 1 or 2. It doesn't fall in the family of integers. Okay, and we'll see why that's important a little bit later on. So we're gonna do this. We're gonna solve for this by doing an example. So here in red, I've written a special case of this general blue form, and the integral we're gonna solve for is the integral from 0 to infinity, x to the alpha over x squared plus 1. So 1 over x squared plus 1 is the rational function, and x to the alpha is this x to the p. In addition, alpha is within this range. It's less than 1, but over 0. Okay, so it's a real number. So the next thing that we're going to say is different is the contour or the curve that we're integrating around. Before we choose the curve as the upper half plane. So we had the curve as it started at -r, went to r, and looped around back to the semicircle back to -r. It just dealt with the upper half plane. Or in the previous video, we dealt with just a circle as our curve. This curve is sufficiently more complicated, so it's going to take a little more work to understand, but it is very, very interesting. So this is called the keyhole contour often, and here's how it works. So we're going to start right here. So we're going to start at this point here, and this point is going to be epsilon, which is going to be just some general small number. And the first part of the curve is going in a straight line, so we're actually traveling on the positive real axis. I know it's drawn above the real axis, but that's just to show you that there's two different ways you're going. So we're traveling from epsilon on the real axis all the way to r, some bigger number on the real axis. Then we're going the whole circle of radius r, the entire circle, okay? All the way around. We're going back to where we had started the circle, and now from here we're traveling back on the real axis from r back to epsilon. So we're traveling in the opposite direction back from r to epsilon, and then from here we have to do one last part of the curve. We're traveling on the circle of radius epsilon in the clockwise direction. So this is positively oriented. This whole curve, the direction we went, is positively oriented because it keeps this inside, this whole part right here, always on the left. Okay, so this is called the keyhole contour. You can see kind of why, because it looks like a key shape could fit right here. So the important thing to note is that even though I drew these green lines, which are now gray, above and below the real axis, they're actually on the real axis. I just drew them there for the sake of showing how the direction goes. Okay, so the next thing we do is a little bit of algebraic manipulation. So our integrand is x to the alpha over x squared plus 1. We're going to transform this to z's. So we have z to the alpha over z squared plus 1. Now the numerator, we want to change it in some form of e to the power of something. So I put it as e to the power of alpha natural log z, and confirm that that's okay, because e to the natural log z is just z, and z to the alpha is exactly what we have here. So the denominator remains untouched. Now, if you remember back from the logarithms video, we have natural log z equals natural log of modulus z plus I theta, where theta is the angle that z makes with the positive real axis. So in this case, we're going to take the angle from 0 to 2 pi. So there was a function that we used before that had big log with a capital L. That had the theta had to go from positive pi to negative pi, or negative pi to positive pi. But in this case, we're not going to be using this. We're just going to use a general branch of log z where theta goes from 0 to 2 pi, because that's going to help us for the purposes of this problem. So that means that the lower bound of theta is 0 and the upper bound is 2 pi, which means it's single valued, because remember, the only reason this would not be single valued is if we were allowed a big range for theta that meant that you can have multiple values when you plug in different values of z. But we're not allowing that. It's only single valued. So there's only this small range, this range of size 2 pi. So this entire, this ln z that we defined right here is in fact single valued and analytic on this domain that we have defined right here. Okay, so with that in mind, let's go ahead and set out to solve this problem. So k, I'm going to define k as the keyhole contour. So wherever you see a k, that just means the whole keyhole contour. Okay, so we have the integral of e to the alpha ln z over z squared plus 1 of k dz is equal to, by residue theorem, 2 pi I times some of the residues of this this integrand, z sub k, where z sub k are isolated singularities inside k. And notice that in contrast to before, when we had the upper half plane, we only looked at residues, we only looked at isolated singularities were in the upper half plane. But in this one, since we're encompassing all of this, and we are in fact going to take this r to go to infinity, and this epsilon will go to 0. So in fact, you're looking at isolated singularities that are in a much bigger area. They can be anywhere inside this gray area, which is going to expand to infinity in all directions. Okay, so you need to choose different isolated singularities, make sure they're inside this range, this region, when you are using this integral. Okay. So that equals to what? So what are the isolated singularities of this function? That's going to be when the denominator is 0, because the numerator we said was analytic, so we don't need to worry about that. We need to worry about when the denominator is going to be 0. So we see that that's going to be at I and negative I. And which of these, if any, are inside our loop? So we see that I would be right here, negative I would be right here. And if R gets really, really big, then this I and negative I easily fall inside this area. We see that they're already inside this area here. So in fact, we have to consider both of them, okay? So we're going to have to consider both of them. And so the answer will be 2 pi I times the residue of the function at I plus the residue of the function at negative I. So the next thing we'll do is compute these residues. So let's look at for I. So the residue of the function at I is what? So we've been doing this already 3 or 4 times. It's just going to be the numerator evaluated at I divided by the derivative of the denominator to I. But the thing we have to be careful of is what's the numerator and denominator in each case. So for the first case, the numerator, we're going to take it to be I. So the numerator is going to be this part right here, because that does not include this part, which would cause the numerator to be undefined, which we don't want. So this gray circle, this gray area, what's inside this gray box right here is going to be our numerator, and our denominator will just be this z minus I. So if we plug I into here, we're going to get e to the alpha natural log I divided by 2I, and then if we take the derivative of this, it's just going to be 1, so it doesn't affect anything. So in the end, the residue is going to be e to the alpha I pi over 2I. And how did I get that? Well, natural log I, we have the formula for natural log here. It's going to be natural log of modulus I, which is 1, so natural log 1 is 0, so that cancels out, plus I times theta. And since I is up here, what's the theta associated with it? Well, it's going to be pi over 2, because starting from the positive axis, we go a angle of pi over 2 to get to it. So that's why this is pi over 2 up here, divided by 2I. Okay, now if we do the residue for the other one, at the other isolated singularity at negative I, it's going to be the same thing. So I just put different functions C and D. So C, the numerator, is going to be what? Now the numerator is going to be this, because we don't want negative I to do anything crazy to this. So we leave the other part as the denominator, which is where it's going to have a problem. So we put negative I into here, and we get e to the alpha natural log negative I divided by negative 2I. And again, when we take the derivative of this, it's going to be 1, so it doesn't affect anything. And so when we have natural log of negative I, what's that? It's going to be the same thing. So again, this ln modulus of z will go away, and then we have I theta. What's theta in this case? It's going to be pi over 2, pi, 3 pi over 2. So we have to go 3 pi over 2 to get to there. So it's going to be negative e to the alpha I 3 pi over 2 over 2I. This negative is there because that's a negative 2I. Okay, so now we have the two residues, and then we want 2 pi I times the sum of the residues. After we do the algebra, we get that it's pi e to the pi over 2 I alpha minus pi e to the 3 pi over 2 I alpha. Okay, we are not done. We have just found the sum of the residues times 2 pi I. So our next step is to write out this integral k and write it into all of its components. So again, we have the integral over the keyhole contour of e to the alpha natural log z over z squared plus 1, and it's broken into 4 parts. So the first part was, let's go back to the picture and follow along. The first part was from epsilon to r, so that's going from epsilon all the way to r. And we can put x's there because it's just traveling on the real axis, so everything is real. E to the alpha natural log x over x squared plus 1 dx. The next part was you had to go around the circle of radius r. So we have modulus z equals r, and we have the same function in terms of z, dz. And I put an asterisk because we'll be estimating that in just a second. Now the next part is traveling back from r to epsilon. So we're going to go from r to epsilon. Notice it's reversed here. And here's a little nuance that we need to clear up. So here I had e to the alpha natural log x. Here, why do I have e to the alpha natural log x plus 2 pi I? That's kind of weird. Well, the reason is because it goes back to this formula right here. Natural log z equals natural log a modulus z plus I theta. When we're traveling from epsilon to r, what is our theta? Well, our theta is actually 0, right? Because we have not even left the positive real axis. So theta that is 0. We can just get rid of it right there. And we just have natural log of modulus z. But natural log of modulus z, anything on the real axis, is we don't have to even put the modulus. We can just put natural log of z because they're just real numbers. But here's the small thing that happens. Next thing we do from here is we travel around this whole circle, just like this. And while traveling it, we have changed our theta from 0, and we travel around the whole circle. Now our theta is what? It's 2 pi because we've done a full rotation. So now we have to think of theta as 2 pi. So now when we go back from r to epsilon on the real axis, going back in the negative direction, natural log modulus z doesn't change. They're still all real numbers. But then we have plus I times 2 pi, which is why I have e to the alpha, and then instead of just putting natural log x, I put natural log x plus 2 pi I, because when we have e to the alpha ln z, natural log z is going to be natural log x plus 2 pi I, because our argument, or our angle, is now 2 pi. Okay, so that's a small nuance, but it's going to, if you don't do that, you're going to get the answer wrong in the end, which you don't want. Okay, so the last step is to go around the circle of radius epsilon, and that's just given here. So, and that all equals pi times e to the pi over 2 I alpha minus pi e to the 3 pi over 2 I alpha, because that's what we found using residue theorem for our main integral right here. So next thing we're going to do, we have to do two estimates. The first estimate we'll do is of this integral right here, where modulus z equals r. So it's not too bad. We're just going to use the estimation formula again. So here we want to find the estimation for this integral. And I'm going to revert this e to the alpha natural log z back to its original form, z to the alpha. Okay, we want to find the estimate of this. This is going to be less than or equal to the maximum value of the modulus of the integrand when z is on the big circle. Okay, because this is done on the big circle, times the distance of the big circle, which is 2 pi r, because that's the circumference. Okay, so note that that's different from just the pi r from the previous video, because that was just half a circle. Now the next thing we want to do is try to find this maximum. What is this maximum equal to? So what we can do is we can take the modulus of the numerator and the denominator. When we do it for the numerator, we get modulus z to the power of alpha, and the denominator we have modulus z squared plus 1. So modulus z is what? Well, it's given as r, right? So it's going to be r to the alpha, we see that, over 1, and then I'm going to split this up differently. It's going to be 1 over modulus z squared plus 1. This is less than or equal to, again, this r to the power of alpha remains, and I'm going to split, I'm going to actually factor this a little bit. So I'm going to write z squared plus 1 equals, I'm going to factor out z squared, and what we're going to be left with is 1 over 1 plus 1 over z squared, right? I can do this because all I've done is just factor out z squared. If you multiply back, you're going to get the exact same thing. So now I'm going to take the modulus of each of these terms right here, and modulus of z squared and modulus of 1 plus 1 over z squared. Now what's modulus of z squared? Since modulus of z is r, we're going to get r to the alpha over r squared, and we're left with 1 over modulus 1 plus 1 over z squared. Now this looks kind of horrendous, right? Because we don't know how to estimate this. Well, the fact is we don't really need to. Because think about what you're doing. You're trying to find the maximum value of this on the circle, right? So let's go back to our picture. You're trying to find the maximum value of this on the big circle. Well, the truth is you don't actually have to find the maximum value. You just need to know there is a maximum value, right? Pretend you're traveling on the circle, and every time you get to a new point, you're plugging in that z right into here, and you're finding the value. And eventually, after you traverse the whole circle, you're going to have found some maximum value, right? Let's just say it's right here. So since there's the maximum value, well, what is the maximum value? It's just some constant c, and you're always going to be able to find some maximum value because this is a closed form right here. So we're going to just arbitrarily say that maximum value is just some c, because we know there has to be some maximum value. So we have r to the alpha over r squared times c. So this indeed is the maximum value right here that we were looking for. So what we're going to do, that integral right here, is less than or equal to r to the alpha over r squared times c times that 2 pi r. So times that 2 pi r, and since we have r to the alpha here and r here, we can write r to the 1 plus alpha times 2 pi c over r squared. And now let's note something from the very beginning. There was a reason we had alpha less than 1 or greater than 0. So let's just say alpha is 0.5 for a second. Then this would be r to the 1 plus 0.5, or r to the 1.5. And 1.5 is smaller than 2, so that means this denominator grows much, much faster than the numerator. And as r approaches infinity, this will get huge, and this will not be able to keep up, and this whole term right here will just zero out. In fact, you can choose anything in that alpha range that we had defined before, and it'll do the same thing. Because the maximum of this is, the number that it cannot reach would be 2. This can't be r squared because alpha has to be less than 1. Okay, so that means that this goes to 0 as r goes to infinity, and indeed we are making r go to infinity, which means that this integral right here, this asterisk one, is going to, thankfully, cancel out. It's going to go to 0 as r goes to infinity. Now that still leaves us the problem of this purple integral right here, but we're going to do a similar process on the back. So this purple integral is the one around the small circle with the radius epsilon. Okay, we're going to do a very similar process. So again, we want to estimate that integral. It's less than or equal to, and then we're going to revert this back to its original form, z to the alpha, and this is less than or equal to the maximum value of z on the small circle and the modulus of the integrand times the distance of the small circle, which is 2 pi epsilon. Okay. Now this is less than or equal to what? So we can just follow similar steps as before. So if we take the modulus of the numerator, it's going to be modulus z to the alpha. What's modulus z? It's going to be epsilon. So it's going to be epsilon to the power of alpha. And then what are we left with? We're just left with modulus 1 over 1 plus z squared. And again, what we can do, we can go on the small circle that we have here, and we can say, okay, I'm traveling across it, and every time I travel to a new point, I'm going to evaluate the value of modulus 1 over 1 plus z squared. And there's going to be some point where I find the maximum value, let's just say it's here, and I'm just going to arbitrarily call that c. Okay, so indeed, the maximum value of this is going to be e to the alpha times some, whatever maximum value this has, c, times 2 pi epsilon. So this, we have e to the alpha here, e here, we can write 2 pi c, e to the alpha plus 1, okay? And now we want epsilon to go to 0, right? Because in this picture, we wanted r to go to infinity. We wanted to get to huge, but we wanted epsilon to go to 0 because we want our integral to be from 0 to infinity. So as epsilon goes to 0, this term right here goes to 0, and 0 to the power of maybe like 1.5, 1.3, whatever this is, it's going to go to 0. Okay, so again, the very good thing we found out was that this integral also cancels out. So since both circle integrals cancel out, we're just left with the integrals on the line segments, and now we just have to deal with that a little bit. So that means that if we plug in, we have 0 and r here. We have epsilon and r here. This epsilon goes to 0, we said. Goes to 0. This r goes to infinity, we said. Infinity. Now the only problem here is that this limit is from 0 to infinity as we wanted, but this is from infinity to 0. Easy fix, we just make this positive sign and negative sign and we flip those, okay? So that's exactly what I did here. I went from 0 to infinity of the original dx minus, so this became a minus sign, and I was allowed to put this from 0 to infinity. And what I did was, since this was e to the alpha times this quantity, I just split it up. So I made it e to the alpha natural log x times e to the alpha 2 pi I. Just like here. And then what we just do is, there's one part, since this is in terms of x, and this term right here, e to the alpha 2 pi I, has nothing to do with x at all. It's a constant. We can just factor it out. So now the common term is going to be the integral, which we factor out, and we're going to get a 1 after we factor that out from here, and we're going to be left with this term, the e to the alpha 2 pi I, after we factor that out from here. We're going to have that here. And that all equals to this term right here, because that's what we found was the sum of the residues times 2 pi I. I'm going to factor the pi back out, and we'll get that it's equal to this. So now after all that work, let's notice something. This right here is the integral we want, right? We want the integral from 0 to infinity of e to the alpha natural log x, which is just really x to the alpha, over 1 plus x squared dx. So all we have to do now is take this right here and divide it by that, which I've done right here. So we have this integral, I cleaned it up, put it back into its original form that we wanted it in, and we take this quantity right here, we divide it by this new quantity right here, and we have our answer. The answer looks pretty ugly, but it is the answer. It's going to be pi e to the pi over 2 I alpha minus e to the 3 pi over 2 I alpha, all divided by 1 over e to the 2 pi I alpha. Okay? So, the reason we didn't want alpha equal to a integer, or for that reason the general p equal to an integer, is what if p was an integer? Let's just say it was 2, so alpha was 2. 1 minus e to the 2 pi I times 2. This is going to be 1, and this is 1. So 1 minus 1 is 0, so we have a 0 denominator, so this integral doesn't really exist. So as long as we don't have that, we're good. So alpha is not going to be an integer. Okay, so that's how you do this. Let's recap. Let's do a recap. So the difficult part here is just, difficult part is choosing this contour. It's looking at this thing and saying, okay, I need to use the keyhole contour. But once you do that, everything will flow. You'll need to find the residues. And then after doing that, you'll need to write out your integral as the sum of all 4 of these integrals. And then if your professor wants you to, you'll have to estimate these two and prove that they equal 0, just like we did here. But in general, they're going to equal 0. And then the last thing to do is just algebraic manipulation, where you factor out this term and you divide what you found, the 2 pi I times the sum of the residues divided by that term, and you should get the answer. So it is a lengthy process, but worth it in the end.